Alright, so here is the video for week 12 notes, the notes that we did before break. Keep in mind we didn't get through all these. The notes that we did not get through will not be tested. We're going to look at acid bases, equilibrium, and kinetics. So make sure you know the properties of acids, that they have a pH below 7, and then just some other things that are associated with them. Also know the dissociation of an acid. So it can form H plus or H3O plus. So one example of an acid, and this is going to be a strong acid, which we'll talk about in the next slide. That's one way to draw the dissociation of an acid in water. So this is an acid dissolved in water. Notice how it forms an H plus. And now if the other way that HCl water is a liquid, will dissociate in water as H3O plus, AQ plus Cl minus AQ. And so water is a liquid, and we form the H3O plus. So weak acid versus strong acid. Now this is something that I think most students are doing pretty well with. So if I said something is a weak acid, I can just be generic. Well, I'm going to pick a non-generic one. I'm going to pick HNO2. So if this is a weak acid, I say this is a weak acid. Draw the dissociation of it, maybe reacting with water. So if it reacts with water, it forms an H3O plus. H3O plus is an aqueous, and NO2 minus. Notice here we have that double arrow. And just like the one that we did on the last page, those are strong acids. So if it is a strong acid, there is not a double arrow. It's not in an equilibrium state, and meaning the reaction does not happen both ways. If something's strong or something's weak, the reaction's happening back and forward, meaning this NO2 is still in the solution and is not fully disassociating to that H3O plus or that H plus, meaning some of it does not break apart. Same thing with bases. Know the trends. Bases always form OH minus when dissolved in water. And we have a strong base. So let's say it's NaCl, no NaOH. And again, I'll tell you, well, yeah, if it ends in an OH, it is strong. And if it ends in like an NH3, NH2, NH, and then sometimes even just N, it is weak. Now these are a little bit different to draw. So we have a strong base. Notice we cannot react that with water. So this strong base does not react with water. And also it starts off as a solid. So if I brought out a strong base and I said dissolve this in water or make a 3 molar concentration or something, it's going to be in a solid. And that's just going to form Na plus AQ and OH minus AQ. Now a weak base has that NH3 at the end. So I'm just going to pick a random one. I'm just going to pick anything. And I say this is a weak base. Now there's no way that this is going to form an OH minus in water unless if we react it with water. Because, and I'm going to draw the double arrows because it's weak, C2H5, NH3, AQ. Now it's a plus on that 3 because it gains a, and then OH minus AQ. And so we have, this is AQ as well. So the weak base is an aqueous, the water is a liquid. So look at the trend. Now keep in mind that the right side, a base always forms at OH. A strong base can't react with water. A weak base has to react with water. And because that H2O is giving up an H plus, the weak base becomes that plus. And so it gains that hydrogen or that proton, which hydrogen at higher levels is called a proton. So a proton is a positively charged molecule, and therefore that's why it's all positive. All right, this simulation I'm taking off. Now these here, you're going to get some equations here. You're going to get those 4, and you're going to have to be able to, and I know we've practiced, or you've practiced a bunch in class on the homework, but you're going to get these 4 equations, and you're going to have to know how to do the anti-log, which we'll do here. And so again, I will give you these here, Ka times Kb we don't need, Kw, and so here we have negative log. So if pH equals the negative log of concentration of H plus or H3O plus. Remember, H plus and H3O plus are the same thing. And molarity means concentration, or molarity means brackets, means concentration. So the opposite of that log is that thing over it. So to go from pH, so let's say if we have to find the concentration, so if we have the pH is 2.31, we have to find the concentration of H plus. It'll be 10 raised to the negative 2.31. And there's going to be 2 sig figs. There's 2 sig figs after the decimal. And it's going to end in big M. You need units on it. pH, no units. And then molarity, concentration, blah, 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 is big M. So sig figs, some teachers skip it in pH. I have before, but it's really not too tough. So let's say if you're asked for the pH of 4.31 molar HCl, there's 3 sig figs, so the pH is going to be, the pH is going to be huge. Don't actually type this in your calculator, or it's going to be extremely small. It's negligible. So, but it's going to be 3 decimal places. So I'm going to do an example here. What is the pH of 0.20 molar NaOH? I'm going to take the negative log of 0.20, and I get the POH, because this is a base, the negative log of OH minus is POH. And I get 0.698. So it's going to be 2 sig figs here after the decimal, 0.70, and therefore the pH is going to be 13.30, because pH plus POH is 14. So I'll do one more example here with an acid that would actually be real. What is the pH of 0.531 molar HCl? Now, because it's H, we know it breaks down to H plus and Cl minus. So if we take the negative log of that molarity, we get pH. So negative log of 0.531 is 0.2. And so we have 1, 2, 3 after the decimal because we have 3 sig figs there. And no units on pH or POH. And so if, all right, here's just an example. Has a POH, so pH plus pH is 14. So a lot of students got this wrong on their post-lab quiz. So in a sense, 14.00, it's an exact number. So we're going to go 14.00 minus 3.19. And you're going to have the same amount of decimal places after. So a lot of students went to 1 or I don't know. But when you subtract, you go with the least amount after the decimal. Both have 2 after the decimal, so that the answer is going to be have 10.81, and so it's going to have 2 after the decimal. So pretty easy if you know how to do the so here we have to find concentration and we have to find pH. Remember, pH plus POH, and let's just write 14.00. And then we also know that concentration of H3O plus times concentration of OH minus is 1.0 times 10 to the negative 14th, meaning all pHs are going to have 2 decimal places because there's 2 sig figs here. Whereas here, that pH has 2 decimal places. And because the amount of decimal places is equivalent to the amount of sig figs in the question, so we got 1, 2, 1, 2. And simply H3O plus is also the same as H plus. So in a sense, negative log of H3O plus equals pH. Just like negative log of H plus is pH. So I'm just going to enter these negative log of 7.3 times 10 raised to the negative 7th. So we have pH of 6.14. And then if we're going backwards, and we want to find here, I'm going to type in, so just make sure you know how to do it. 10 raised to the negative 11.08. And I get what? So 2 sig figs, 8.3 times 10 to the negative 12th, big M. So moles per liter, same thing as big M. Big M equals moles per liter. And here we have, just keep in mind that concentration of H3O plus times concentration of OH minus equals 1.0 times 10 to the negative 14th. We have 1 sig fig there, so 1.0 times 10 raised to the negative 14 divided by 2 times 10 raised to the negative 11th. And so 5 point, it'll be just 5 point or 5. 1 times 10 to the negative 4th, big M. So here we have to calculate the pH of a strong acid solution. We'll do 1 with acid and 1 with base. Remember, pH equals the negative log of H plus. Concentration equals big M, which is moles divided by liters. So there is some work you have to do here. We have a amount of milligrams. So that's 0.701 grams of HCl. We have to convert that to moles. And to do that, we divide by molar mass. So molar mass of hydrochloric acid is 35. I'll just look it up here. 35.45 plus 1.01. So we have 36.46. So that's how you find moles, not too tough. 0.701. So you're going to have to find the molar mass divided by 36.46. And so we get moles equals 0.0192 over liters. When you have milliliters, you move the decimal 3 times, 3.90. So I'm going to divide that by 0.390, and we get the concentration, the big M, equals 0.0493. Because we have 3 sig figs there, 3 sig figs there, and we're going to have 3 sig figs in the answer. And therefore, we're going to have 3 decimal places when we take the negative log of this. So the negative log of 0.0493 is 1.307. So that is the pH of that solution. I realized in the last video I made a mistake. It was hydroiodic acid and not HCl. But yeah, so make sure you read it carefully. So anyways, now we have to find the pH of a strong base. Now this is the same thing, and it's something you can practice, so I won't go through it. But remember, molarity equals moles divided by liters. And this is sodium hydroxide, so you're going to have to convert again from so that starts off as a solid, breaks down to Na plus, aqueous, OH minus, aqueous. And you're going to have to take the negative log of the concentration. But since it's a strong base, remember you're finding POH here. And you want to find pH. So you're going to have to subtract from 14. Hence, once you find the concentration, if you take the negative log of that concentration, you're going to get 0. So how many sig figs we got? We got 3 sig figs there and 2 there. So we're going to have 2 decimal places. You're going to get 0.93. That's the pH. And since this is a strong base, or no, that's a POH, I'm sorry. Since this is a strong base, that's what we calculated. So the pH in the long run is going to be 13.07. We have 2 decimal places because we have 2 sig figs, 3 sig figs. We go with the least amount, no units. And another way you can test this out is by going, okay, well, it's a base, therefore it needs it's going to have a pH greater than 7. So for equilibrium, there's not going to be a lot asked on it. You're going to have to write equilibrium equation. And so we have K equals concentration of HI squared over HI. And so that is just the equilibrium. So keep in mind this equilibrium. This reaction is happening both directions. So in equilibrium reaction, so just like a snowball fight, snowballs are going to the right and to the left. And what you're going to have to do is play with this K value, determine what the K value means. So some math, but remember, once a reaction is at equilibrium, the forward reaction is equal to the reverse reaction, no matter how big the K value is or how small the K value is. So this is just a generic view of K, but sometimes just writing out ones make it easier. So here, I think there was a mistake on one. Someone pointed out a mistake. This looks right. Looks right. So I don't know where the mistake was. Yeah, I don't see it right now. So ignore what that KC is, but it's always just going to be a K. And so if K is high, so keep in mind you have, let's say, A plus B is forming AB. And we always know it's products over reactants. So let's say AB is very favorable. That means that AB, its concentration, is much higher than A and B. And so the products are favored, or there's always more products than reactants. And just like the opposite of it is, since K is products over reactants, let's say we have 1 AB to every 1,000 A's and B's, we're going to have a very low number. So therefore the reactants are favored. Now, even if the concentration on one side is, so these are concentrations, even if one is much larger than the other, the reaction's going back and forth at the same pace. Meaning, like if you have 1,000 people on one side in a snowball fight and one person on the other side, they might be throwing a lot of snowballs initially, but this person on the right side, on the product side, can only throw one snowball at a time. So they can only throw one snowball back because that's all they have. You're going to have tons of snowballs on this side, but the reaction is always going forward and reverse at the same pace, the same rate. And then lastly here, if it's about 1, if K equals products over reactants, you're going to have about the same amount of products as reactants. So neither are favored. Same products as reactants. So this is what I have been saying. It happens forward as fast as it happens backwards. And forward reaction is equal to the reverse reaction. I'm just going to go through the calculations here because I remember I didn't really give us a slide. So let's say A plus B forms C, and this is, or AB, this is an equilibrium equation. And let's say K is 50. There's no units on that. If we're to reverse that, K is now going to be 1 over 50. So if we reverse the reaction, K value is 1 over the K. So meaning the opposite of K. So okay, so then we have, let's say if we doubled everything, K is going to be 50 squared, just like if now let's reverse it. And triple it. K is going to be 1 over 50 cubed. So if you triple the concentration, it has a direct rate on the K. If the products become the reactants and the reactants become the products, it's just 1 over K. So this is just an example of writing an equilibrium expression where K is products. I'm sure this was probably a headache to enter in Alex over reactants and so forth. And if we have a huge K, products favored. This one just has 1, so there's not going to be any superscript. Then here, if K is very small, I always just write P over R. We know this number has to be big, so reactants favored. And the math of K we just talked about. So like here, if we're to reverse this, 2HI H2 plus I2. If we're to reverse it, it's going to be 1 over that number. I think the key would be, and this is no longer as a base, so notice how there's no units on that. The key would be just using the right parentheses. So we got 1 divided by, or being able to use the parentheses correctly. It's okay here is huge, which makes sense because this is now products over reactants, and it's going to be the opposite of it. So boy, so this is like 2.6 times 10 to the 1, 2, 3, 6, 8. And let's say if we reversed it and we tripled everything. So let's say now it's 6HI plus 3H2 plus 3I2. They're always going to be tripled. So now we're going to do 1 over, no, that's already reversed, my bad. So it's going to be now this number of 2.6, because keep in mind we already reversed it here, times 10 to the 8th raised to the 3rd power. 2.6 times and I get 1.8 times 10 to the 25th. And so playing with K is the key here. Here's some Alex. The only one I'll go through because we already did is down here and you can practice it. Now K is either going to be really big, really small, or close to 1. And if it's really small, remember it's products over reactants. If it's really small, then we have a lot of reactants. Therefore, there's not going to be a lot of NO in it. So just like I have to write Liouville, I always have to write products over reactants. And then which number is going to be big? This one's big when the K value is really small. But here the K value is close to 1. So there's not going to be very little of either, because if you take Chem 2, you're going to see K values either extremely huge or extremely small, and then like 5 or something. And even if it is 5, it's not like there's very little of something. And so here you just have to play with K. We have the first reaction reversed, so it's 1 over 1.4. The second reaction we have doubled, so it's 1.4 squared. So this here is the last thing that will be on the test, and it's essentially just one thing, and it's from kinetics. And I'm going to put up, now everything after that is not on it. We didn't get to that stuff, and we have to cover 2 more things. So this is all we're going to do with kinetics. And we see here, so we covered acid base, equilibrium, now kinetics. Kinetics is like a strong acid or a strong base. Equilibrium was like a weak acid or weak base, where we have the double arrows. But kinetics has just an arrow in one direction, meaning maybe it's more like a reaction that you have thought of yourself, or not thought of yourself, but a normal reaction that you thought reaction was. And I'm going to go through these and make sure you know how to verbalize or identify or draw these different things. So kinetics is the measurement of a rate of a reaction that is not reversible. So on that prior page and then in class, used an example of 2 red plus 1 blue forms essentially R2B. Now, if concentration increases, so for example, if we had reaction 1, this many red and blue, and then we had reaction 2, same size vessel, and we have, we draw less. So as concentration increases, so does rate of the reaction. And think about that logically. So this is going to have a higher rate, meaning the reaction is going to happen quicker. If 2 red have to bump into 1 blue for the reaction to occur, the more red and blue you have in there, the faster the reaction is going to take place. And that's somewhat logical, but also keep in mind what is more important here, the red or the blue. Now, if 2 red and a blue have to hit each other at the same time, the red is going to be exponentially more important. So if we increase the concentration of red, the rate's going to go up quite a bit faster than if we increase the concentration of blue. And that is because, the reason for that is because if it was just red and blue, and that's all that had to happen for a reaction to occur, it's going to be pretty simple. But the chances that 2 red and 1 blue hit each other to form this, it's going to be, decently small if you really think about it, unless if you have a ton of red in there. So the amount of red that is needed to, or if you increase the concentration of a reactant, so if we have 2 red plus 1 blue equals R2B. If we increase concentration of red, rate in kinetics increases a lot. And then if we increase concentration of blue, it's just going to increase less. Still increase, I don't know why I'm writing rate, or increase less. And so the other thing that you have to know from this is As speed goes up, so does the rate of the reaction. So again, that sort of makes sense. If we have a reaction here, and we have blue, we have red. Let's say they have to hit each other for the reaction to occur. And so you're heating this up. And the molecules are going to move faster the higher the temperature is. And so as speed increases, there's more collisions, and the collisions are harder. So maybe sometimes, or not maybe, but sometimes a red and blue might hit each other and there's not a reaction. So more kinetic energy, so more reactions take place when they hit. So there's something called an activation energy. I won't test activation energy, but I will ask about this. Why does speed increase the rate of the reaction? And if they hit each other harder, there's a better chance of it overcoming this so-called activation energy. So one last thing is volume of a container plays a role in a chemical reaction. And again, that's going to be rationally based. So I'm not looking for numbers here, but rather a rational understanding of it. So again, if we have a larger, smaller container of red and the same amount of red, and then let's say 2 blue, and if the container is smaller, so volume goes down, pressure goes up, and rate also increases, because again, there's more collisions. Now, they're not going to hit each other harder in here, but they are going to hit each other more frequently. So just because I'm decreasing the volume doesn't mean I am heating it up. And so if volume goes down, pressure goes up, there is, you're just in a smaller room. So if you put a bunch of boys and girls in a large room, there is going to be less collisions between a boy and a girl than in a smaller room. So if you put them in a real small room, they're just going to be bumping into each other all the time. So more collisions, but here there's really only one reason compared to 2 reasons for speed. All right, so that's it for kinetics. The rest of this is not on here, so we did not get to it. And, this is how to write a rate law for, but whatever, it doesn't matter. So yeah, that's it. And then I will make a video for this week as well, but the rest of this is not on.